University of Texas. So with no further ado, Lorenzo Sadun.
Pleasure to be back here in Arkansas, talking about how the world fits together. So what I'd like to do is I'm going to talk a little bit about what the world is made of. I mean, we're different kinds of matter, and it'll turn out that some kinds of matter are pretty easy to understand. There isn't a big mystery about them. And then the other kinds of matter are the things that people don't talk about much. People pretend that we understand this and that's everything, and so we don't have to worry about anything else. But no, there is other stuff. There are mysteries about how do the other forms of matter actually come to be, and how do things combine in interesting ways. And at first glance, the laws of physics don't seem to explain those. I'm going to switch gears to tilings, because tilings give us a model of how things fit together. That if you think of the basic building blocks of nature, you can think of them as tiles, and then the forces between them are like rules about which tiles can fit together with which other tiles. And you could imagine, an atom isn't really a tile with a little notch pointing this way, and another tile has a notch pointing that way. But you can say that two atoms can bond together, and you could model that by having a tile that has a little prong on one that fits into a little groove on the other. So we'll see that tilings provide a very useful model for the way that materials fit together. And we're going to do that first in one dimension and see what some of the structures are there. And then we're going to go to 2 dimensions. And we'll see that within the world of tilings, there's sort of this explanation for how do these other forms of matter actually work. Of course, that's still in 2 dimensions. And we're going to talk in particular about some constructions by Raphael Robinson and Shahar Moses. And I'm going to spend some time on this particular construction and a particular hierarchy and see if we can understand that example really well, because it's a nice example of the kind of ideas that I'm going to be talking about. And I'm not saying that matter is actually composed of the particular structures that appear in Robinson's model and Moses' construction, but this shows how the kind of structure that we're talking about can come about. Now, of course, we live in 3 dimensions, not in 2 dimensions. So I'm going to talk a little bit about what extra features we get from the 3rd dimension. And in some ways, we've got a 4th dimension, because we've also got time, and things change over time. And so the fact that there are 3, and in some sense 4 dimensions to play with, gives us more ways of understanding the world. And finally, if there's time at the end, we've got enough of that 4th dimension, then we're going to talk about chaos and how tilings and tiling spaces are related to the phenomenon of chaos. So it's a fairly tall order, but we'll try. So let's start off with the kinds of materials that you find in the world. So one kind of material that you'll learn about are fluids. If you took a disembodied brain, the sort of thing that you saw in the old Star Trek or something, and you tried to ask them what sort of matter would there be in the universe, they would probably think of gases. Fluids are pretty simple. You've got a whole bunch of particles zipping around, each one going its own way, and none of them paying attention to any of the others. It's all incredibly random. And that randomness means that if you want to understand what one molecule is doing, you can't. It's just too complicated the way that it can possibly bounce around. But you've got millions and billions and trillions, quadrillions, and actually it's much bigger than that. You've got a huge number of particles, and so you can use the laws of probability and statistics to explain what is happening in the aggregate. So I can't tell you what the 3,757,356,842nd air molecule in this room is doing. I've got no idea. But I do know that the density of air in that part of the room is pretty much the same as the density of air in that part of the room. So the large-scale properties of gases are really pretty easy to understand, and other kinds of fluids, like liquids, where things can slide past one another, are also of this random sort. You can't say anything very well about what any one particle is doing, but you can say a lot about what the entire thing is doing. And in this sense, although there are some tough problems in fluid dynamics, the existence of the structure of fluids is no big mystery. And then, what else? You learn about solids. And how do people describe solids? Well, you've got a solid, you've got an atom here, and then you've got another atom here, and then you've got another atom here, and they all lock together in some rigid way, kind of like a brick wall. Now, in some sense, a brick wall isn't all that interesting, because it has some structure. You've got this particular way that bricks line up next to other bricks. But would you learn anything if I showed you a bigger picture of that brick wall? No, you know what's happening in this part of the brick wall. You know what's happening in the parts of the brick wall that are extending out into the next county. All that's happening is happening on a very, very small scale. If you understand what's happening in one little patch, you understand what's happening everywhere. So in that sense, the brick wall is a very simple thing. Just understand a little bit, you understand the whole thing. And zooming out doesn't tell you anything. There's only one scale at which you have to understand things. Think if you've got 1 foot bricks, you want to examine what's happening on the scale of 1 foot, or maybe 2 feet, or maybe 3 feet. But you don't have to look at what's happening on the scale of 100 feet or a mile. Finally, if you move it around, you can get the exact same pattern. If I take the brick wall and I slide it over by the width of 1 brick, I've got the same brick wall pattern. If I take the brick wall and I slide it down by the thickness of 1 brick and over by half the size of a brick, I've got the exact same pattern. So whenever you have this business that you can move it around and get the same thing, we call that periodic. So to my mind, crystals are periodic materials, and they're not all that interesting. And gases are not periodic materials, they're random materials, and they're not all that interesting. Okay, then we got mixtures. Okay, not everything is exactly a gas or a crystal. You have some mixtures, and typically what you have in a mixture is, think of a piece of mud. You've got a lot of little pieces, and each piece might be a crystal, might not, and they're all jumbled up. So it's sort of like a mixture of the ideas of a crystal for each little piece, and a gas for how the little pieces are all scrambled together. So there aren't any really big new ideas for mixtures. If you understand fluids or crystals, you understand mixtures. Okay, so what's left? Everything. Look around you. How many gases do you see? Okay, trick questions, you can't see the air. But, okay, we've got some air, there's some fluid around there. How many crystals do you see? Well, there's some pieces of metal. Metal is basically a crystalline pattern. But I don't see a whole lot of metal in this room. There's some. What about everything else? Everything else is complicated. The really, really important thing about everything else in this room and everything else that you saw on the way to this talk is it's got parts. You've got big things that are made up of little things. And little things are made up of smaller things. And smaller things are made of really small things. And so this isn't like the brick wall. The brick wall, if you understand what's happening at the scale of 1 foot, game's over. You understand everything. But for things that have, but people, or buildings, or anything that makes up the honest-to-God real world, has lots and lots of structure of different scales. You have to understand what's happening at the scale of 1 foot. You have to understand what's happening at the scale of 1 inch. You have to understand what's happening at the scale of 1 millimeter. You have to understand what's happening on the scale of 1 atom. And it's a different story at each scale. There's lots and lots of information. The more you zoom out, the more interesting stuff you see. The more you zoom in, the more interesting stuff you see. Okay, so anything that has all these many, many, many layers of structure, we're going to call that a hierarchical structure. And the fact is, most things in the world are hierarchical. Why? This is a big mystery. I mean, you walk every day and you see trees with branches and leaves and tiny bits. You see hierarchy all through everything that you encounter in your daily life. And the mystery is, how did it get there? So you see people, and well, people have parts. You've got lots of organs that people are made of. And the organs are made of tissues, and the tissues are made of cells. If you look at the cells, a cell isn't just a big sack of chemicals. A cell has a whole bunch of very, very, very definite parts. And here's a part, it's called a ribosome, and that's made up of some big proteins that are locked together in a very, very, very definite way. And a macromolecule like a protein or piece like of DNA is made up of constituent smaller molecules. And each molecule is made up of atoms. And each atom is made up of electrons and neutrons and protons. And instead of thinking it from the top down, I described it starting with people and chopping down. Let's think of the whole thing from the bottom up. I want to examine what's happening at the most basic level. The basic units of the universe are electrons, protons, and neutrons. Unless you go talk to the high-energy physicists, in which case they'll talk to you about quarks and Higgs bosons and whatever else. But for all practical purposes, the basic units of the universe are electrons, protons, and neutrons. Just 3 things.